I'd like to thank everybody for joining our now third session of our spring program for the Virtual Inter-University Symposium on Infrastructure Management. So today we have the pleasure of listening to presentations from Ilia Papakonstantinou and Wang Chen on their research. So each presentation will be about 20 minutes, and we'll have about a 10-minute Q&A session after each, in which we really just want audience participation and just have kind of a conversation about research. And so with that, I'd like to introduce our first speaker. So Ilia has received her PhD in transportation planning and engineering from New York University and holds a degree in electrical and computer engineering from the National Technical University of Athens, as well as a master's in science in engineering systems and management from Madar Institute of Science and Technology on operations research. She currently works as a postdoctoral associate with a team of Professor Samer Madanat at New York University, Abu Dhabi, and her research focuses on highway infrastructure protection against sea level rise, which we'll get a little bit more of today, or maybe a lot more today. And so with that, I'd like to hand it over to our first speaker, Ilia. You can go ahead and share your screen.
Thank you, Andrian, and thank you for the invitation to talk today. So do you all see my screen?
Yeah.
Okay, great. So today I'll talk about our recent work, which is on coastal protection strategies to minimize traffic disruption from inundation due to sea level rise, and specifically the case of Abu Dhabi. I have been working on this along with Dr. Siwe, Dr. Cho, Dr. San, and Professor Madanat. So sea level rise has been unfortunately a real threat nowadays, and a lot of top-notch researchers have been focusing on how this phenomenon will evolve in the future. Here are some predictions from less optimistic to more optimistic about the sea level until 2100. And you can see there is a big difference, but overall a clear increasing trend, unfortunately. This sea level rise interacts with coastal infrastructure and may cause disturbance of operations or even damages in vital parts of the infrastructure, such as hospitals, schools, or airports. And this may also lead to very high costs, like the case of 1996 flood in Boston that ended up in $70 million damages. Specifically for the transportation network that we are interested in, the sea level rise may disrupt links, and this can cause capacity reduction, such as, for example, some lanes closures in a highway, or accessibility reduction, such as closure of a subway station. And all these lead to very significant delays in the network. Now, this phenomenon does not stay at the shoreline, but may be amplified further inland because of rerouting and other network effects. So what we do is a holistic approach that includes first the hydrodynamics modeling, and then using as input the results from the hydrodynamics modeling. We want to see how the transportation network will adapt. So first of all, which areas will be flooded and remove those links, and then how the traffic will redistribute, so do a new rerouting. For this, we use some objectives that we believe are useful for urban areas. The first is the VHT, so aiming to traffic delay minimization. The second is VKT, the distance minimization. And the accessibility, which we look into using the number of vehicles that are able to travel. For this work, we have focused on Abu Dhabi, the capital of the United Arab Emirates. It is located in the Persian Gulf, and it has very, very low elevation. So most of the city is lower than 5 meters above the mean sea level. And it is constituted of a system of islands. So it's like 5 islands, main islands that are connected through bridges. And then there are also smaller islands here and there. Here is a map of the area. And all these parts are islands. You can see here. And everything is connected through bridges. Here, this is the main island. And here we have 3 bridges that connect to the mainland. In this map, we can also see the precincts. So we have used the urban structure framework of the Abu Dhabi 2030 plan for these precincts. We have partitioned in 17 parts, and we consider that each of these parts will be either protected by installing a levee across its shoreline or not protected at all. For notation purposes, this like P01 or P02 means that what is protected. These combinations are protected. Now, let's see the process in a schematic. As I said, first we do the hydrodynamic simulations. This is done by Dr. Cho, who is specialized in hydrology. And then we take these results and we find what is the new, what are the areas that are flooded from the sea level rise. And these floods will cause closure of some links and also isolation of some other links. So we remove all those links that are isolated or flooded, and we end up with a reduced network. For this reduced network, we do a new traffic assignment. Now, the problem here is that we have 17 precincts to protect. So, in fact, if we want to see all the combinations, it's 2 to the power 17. It's very high number. So that's why we explored several cases, starting from protecting only one precinct, and then we were adding according to what was more interesting. To find, our aim is to find combinations that will be the best combinations in terms of congestion levels, so the minimum congestion level. So the first part is the hydrodynamics model. I'll talk a little bit about it, but more information will be in this paper that is published by my colleague, Dr. Cho. So what he does is he explores 3 different models and then combines them. The first is the tidal water levels, the second is the storm surge, and the third is the wave run-up. So the summation of all this will give us the sea level rise in different parts of the Gulf. Now, using these results, we overlay the water levels with the topographic elevation that we have from the digital surface model. And this overlay gives us the areas that are flooded, specifically the links of the network that we are interested in. As I said, we removed from the network all these flooded roads, and we do a new traffic assignment. How we do the traffic assignment? We use STEAM. STEAM is a strategic transportation evaluation and assessment model. It's regional strategic simulator and contains information for 2040, which is for now our aim year. And the good thing is that it considers also changes in land use, of course, not considering the sea level rise, but other things and other strategic decisions. So it has all information about the supply of 2040, like all the future roads and everything. This is a software that is not accessible to the public, but we have access due to our collaboration with the ITC of Abu Dhabi. The metrics that we use, first, so we have 2 categories. We want to quantify mobility and accessibility. For mobility, we use the VHT, the VKT, and the VHT per vehicle. These are for the network-wide situation to capture. And then also we see maps with VC ratio, which we can use to see what happens in individual streets. Now, for accessibility, we use the numbers of vehicles because we consider that it happens a lot that the VHTs and the VKTs are low because actually no cars go on the road because the trips cannot be realized. So this is a measure of accessibility. If the number of vehicles is very low, it shows that they cannot really realize their trip. This can be either because there is no way or because the travel times are very, very high. And usually we use percentage changes instead of absolute numbers, using as base case the best case scenario, which is protect all precincts. Let's see some results. So first, for the hydrodynamics, we see that protecting a precinct may affect the flooding in neighbor precincts. Here is a matrix of changes. We can see that all the columns are the protected precinct. So we can see, for example, here, when we will protect precinct number 6, what will happen in number 1, etc. We see when you protect a precinct, this is good for itself in all cases, but sometimes not as beneficial as expected, like here, for example. And there is also a chance, this chance here, protecting the first precinct, Musafa, increases the inundated area in the second precinct. So this could potentially inundate the transportation network within P2, and therefore we have consequences in the traffic. Now, for the traffic interactions, the situation is not as clear as the effects of protecting individual precincts in the hydrodynamics. This is why we are not looking only in this kind of matrix, but we need to see combinations of precincts. Let's compare the case of nothing is protecting versus everything is protected. So here are two maps that show this case where everything is protected. The green shows what is protected. So here everything is protected, and here nothing is protected. So the pale red is a little bit congestion, but the darker red parts are very, very congested. And the white means that there is no congestion. And the black is there is flood. So the first thing is that in the in the protection case, in the protected case, all the bridges are operative here, but in the case of no protection, there is only one bridge, the Sheikh Zayed bridge, that is accessible. So this becomes a major bottleneck because it's the only route. That's why we have much more congestion here, this very red line compared to here. Also, there is accessibility reduction. That's why the network, if you see, it looks smaller in the case of no protection compared to the case of full protection. And the number of vehicles is approximately lower by 30%. So this 30% cannot have, cannot realize their trips. Despite this, we notice that the total network PHT is higher by 20%. And this happens because of rerouting and congestion. So people, even though less people are out, they will reroute that much that the traffic will be 20% worse. VHT per vehicle also is much higher, is 70% higher. Now, obviously, the P all is the best case scenario, but it's very expensive. P none is the least expensive, but of course, the least is effective. So we want to find strategies that are somehow the best in terms of accessibility and mobility, but not as expensive as P all. Here are the most interesting cases that we found. I will not show all of them because of time, but I will show the most important. So the first three, these three, talk about the east part. So I will show the combination P8 and 9. You can see that we protect similar parts, the green parts, the east side. And we see here specifically when we protect Yas Island and Sadiyat Island, what happens. Still, there is accessibility of the island parts on the east, on these parts, from this side. So this island can be connected to the mainland, but not here. Here, because this is not protected, the bridge is not accessible. So everyone will reroute through here to go to the CBD, which is here. So this bridge that is Sheikh Zayed bridge that we said is always operative is a huge bottleneck. And this is why we have very, very high percentage of increase in VHT per vehicle. This is the case here, but also, as I said, the previous cases are also very, very high. These are actually the highest cases of all that we found. These scenarios yield the worst results in VHT per vehicle. This happens exactly because only one bridge will be open, so everyone will reroute through this. Now, let's move to the west corridor. Here, I will talk about the first precinct here to protect. The hydrodynamic model here shows that even though we protect the precinct, there is flooding from the west. And so the situation is bad, not because of the network effects, but because of the hydrodynamics. The rest of the network is very similar to the case of no protection. The connectivity is bad, as you can see, and the travel times are very high. Now, if we add to this protection part a little more, so we add the bridges protection, precinct 2 and 3, then all the bridges will be operative. And this is good because Sheikh Zayed bridge will no longer be a bottleneck, and congestion levels improve very much. So from 90% in the previous case, now we have 31% more than the case of P-all. And if we add to this only one precinct, precinct number 16, then we see that we have also a very big improvement. So this is the case here. It's actually the best case in terms of change in VHT per vehicle. And the last case to show, here we see that it's a little worse than before in terms of VHT per vehicle, but in terms of vehicles, so change in vehicles, it's much better. So this is the smallest decrease in the number of vehicles, meaning that more people will realize their trips. So that's why we consider that this is one of the best case scenarios. Okay, so to conclude, first of all, we find that it is very important to protect, very critical to protect approaches to bridges, as the bridges themselves, the decks are high, so they won't be, of course, flooded, but the approaches are critical to be protected. That's why the precincts between the two bridges should be protected, because if only one bridge is operational, it acts as a big bottleneck. The second important conclusion is similar. It's a different kind of bottleneck. It's when protecting a corridor that connects islands to, like here in this case, we saw the eastern islands. Then we have only one path to go to the CBD. So again, it's a bottleneck. Now, from this work, we want to extract some more generalized insights so that we use in other regions without, again, running simulations, because these kind of simulations are very time consuming, and specifically for the hydrodynamics part. So if we want to generalize our insights, we could say that areas with islands or peninsulas that are connected with bridges, the protection of these bridges is super critical for decreasing the congestion levels. And the second insight is that we should protect links that create corridors that have not many alternatives for rerouting. So in general, this is actually the outcome. Don't leave a single route, because then everyone will go from there, and congestion levels will be very, very high. This is the end of my presentation. I welcome any questions.
Great. Thank you so much, Ilia. Very interesting. At this point, I'll open it up to questions from the audience.
Thank you, Andrea. Yes, please.
Yeah.
This is a work in progress, but we plan to publish it soon. So any feedback is very welcome for improvement.
I have a question if no one does right now. So again, very interesting, and you know, the methodology is very clear in like from your presentation. So I wanted to know if you had actually taken any values for the costs of protecting different precincts, or if you were merely like if at first pass you were just saying, let's minimize the number of precincts, like one additional precinct is an additional cost, or if specific, right? Like I assume that a precinct that has larger coastline or more bridges might be more expensive to protect than one that has less coastline, for example. Did you consider that, or?
Yes, that's actually a great question. I'll tell you, first of all, what you said is exactly correct. The longer the precinct, the higher the cost. So in this specific work, we have not considered comparing costs, but we have actually another work very, very similar that was done for San Francisco Bay Area. And there we had a Pareto frontier that would show all the costs with the benefit. So it was a benefit cost diagram, and you could see for this specific budget that you have, what is the best thing that you can do. We can make something similar here. We never had information about specific costs, but we always considered that the cost would be like relevant to the length. So in fact, the Pareto frontier had the length, not the cost immediate. But as you said, it is analog. However, and now you also mentioned something about the bridge. This we have not considered. So how to protect, if it's different to protect a part that has a bridge, or definitely depends also on the morphology of the place, because maybe at some areas you need to build something that is more expensive, at some areas it's cheaper. So definitely it needs more information, but a high level analysis would be the length of the levee.
Thank you, that makes sense.
Actually, I can, when you post this video on YouTube, I can give you also the links to the papers that we already published that are very, very similar in this sense, to add them for more information.
Yeah, that would be great, actually. Thank you.
Thank you.
I'll ask you a question, Ilia. And so, I mean, this is, of course, very interesting, and it has very, very clear policy implications. And so I'm curious if the work, if it's made its way either in Abu Dhabi or in San Francisco in terms of these infrastructure investment plans that they are carrying out in terms, in this case, of protection. And in the event that it hasn't made its way, or that some of the investments that have been selected are different than the types of things that the model proposes, can you explain why?
That's actually a very interesting question, Pablo. Thank you for posing this. So it's our wish that they take into account our work. We have communicated our work to all authorities. So for San Francisco specifically, we collaborated with another team who was responsible for communicating our work. And for Abu Dhabi, we were directly in contact with the ministry. So once we have finished, we have already sent them all our results. Now, the problem is that for them, they cannot only consider the transportation network congestion, because there is also important parts of the shoreline that should be protected. So you can say, oh, this part won't affect congestion, so I won't protect it. But maybe it has some vital things in it, so it still needs. But even if they consider this work planning their where to protect, this would be our wish. In Abu Dhabi, the strategic team sees very far, so I'm sure that they will take into account our results in their planning. For San Francisco, our work has been published 2 years ago, but I don't know if there is any action taken until today. But yes, for sure, we have done everything we can to make this, loud.
Other questions from the audience? Okay, I have another question. Yeah, so from what I understand, you model like flooding of streets and road segments as like deterministic based on the absolute sea level rise, right? So the flooding either allowed the road to function or not, but I guess sea level rise could also make certain instances, like basically like certain situations where flooding occurs and knocks out other roads, like in a probabilistic sense. So what would you comment on that? So it seems like, right, we certain flooding would reduce the network and then would likely make the network subject to even further reductions in the event of something happening. Is this something that you looked at as well, or I mean, I guess maybe an extension, or have any insights on?
Yes, actually, that's an interesting future work that we could approach. I have not thought of it, to be honest, in terms of how to apply it, but definitely maybe. So I know that there are ways that you can simulate using probabilities. So possibly this could be an extension, yes. At some point, we were considering to use the user equilibrium with probabilities, but then we abandoned the user equilibrium in general and switched to VISIM at that time. So we didn't follow that. And then now we used STEAM, which is very specific. So you couldn't really mess with it because it is very specific the way it works. But now we are planning to do the same work for Dubai. So we can consider doing this from the beginning.
I see. Yeah, thank you. Yeah,
I'm not sure how to implement, but I have to think of it. But it's very interesting, and always we want to do something new because we have done this work in 2 parts of the world for now, and we want to do it for more. And we always want to add something, a new idea in the new thing. So maybe this can be the next step.
Yeah, I look forward to seeing what comes of it then. Yeah.
Thank you, Andrea.
Yeah, thank you. So I guess with that, there's a chance for one more question if someone has it for Ilia. If not, I'll transition over. So first of all, thank you again, Ilia. And so I'd like to introduce our second speaker. So Wang Chen is currently a visiting scholar in the Department of Civil and Environmental Engineering at the University of Waterloo. And he will be employed as a postdoctoral fellow at the Risk-Informed Lifecycle Infrastructure and Engineering Center at Toronto Metropolitan University. So with the cooperation of Dr. Arnold Yuan and Dr. Ningyuan Li, his research focuses on highway infrastructure system engineering management, particularly in lifecycle costing, lifecycle environmental assessment, sustainability-informed engineering design, data-driven deterioration modeling, maintenance and rehabilitation optimization, and decision-making. Currently, he's working on incorporating deep uncertainties associated with emerging construction technologies and materials into pavement asset management for climate change mitigation. So with that, I'd like to turn it over to Wang Chen for his presentation. So please go ahead and share your screen. And thank you for joining us.
Okay, thank you, Andrew. Can everybody see my slides?
Yes.
Okay, thank you. It's been my excited to introduce my recent research here, and today the topic here is the eco-efficiency assessment of long-life asphalt pavement technologies. This is the basic outline for my presentation. As we know, the sheer stock and rapid growth of road infrastructure takes up a big share of financial investment, and it was developed along with a vaster amount of emissions and the greenhouse gas emission and energy consumption. So therefore, joined by the sustainable development and climate change impacts as to pavement field, long life technology is a promising eco-efficiency solution to respond to such issues. However, a holistic and objective comparison with conventional pavement technologies from the eco-efficiency perspective is still lacking. So, motivated by this gap, our objective is to provide an eco-efficiency framework for long-life asphalt pavement design optimization. And we hope to use this framework to identify the crucial factors and processes that influence the eco-efficiency and assess the adaptability of various alternatives on the different design contexts through a comprehensive sensitivity and uncertainty analysis. So first, I'd like to introduce the pavement design. Based on the research and practice in China, we selected 5 most promising long-life asphalt pavement structures here and compares them with a conventional design. So there are 6 structural design here. That is the full depth asphalt pavement, stick asphalt layer asphalt pavement, and inverted enhanced semi-rigid base composite, and the traditional semi-rigid base pavement structure. And the last one is set as a benchmarking design. As to the pavement design, we consider a typical design parameters. The most important one is the design service life, that is 40 years, and another some traffic demand analysis parameters. The design principle here is the equivalent failure. That is, each alternative can achieve the same service performance within the same design service life. So the structure in the signals design were conducted based on the highway asphalt pavement design specification. After that, we use the standard process-based life cycle assessment approach to conduct the life cycle development impacts and life cycle analysis. We consider here here is a 5-stage, and it is typical procedure, including the material conduction, material extraction, production, and the transportation and the construction, as well as the end of life process. The maintenance phase wasn't considered here because we don't have any theoretical deterioration model and the practice history data. And the life cycle in performance indicators here, we consider the life cycle of greenhouse gas emission, total energy consumption, and life cycle cost. In terms of the quantification, we employ the process-based calculation model and use the quality times the emission factors or the energy consumption factors of the fuel or materials. So from that about calculation method, we can see the environmental impacts contains two indicators, that is the greenhouse gas emission and total energy consumption. To exercise the to evaluate the eco-efficiency more easily, we provide the following types. The first one is the aggregation. That is, we use the social willingness to pay method to monetize both the total energy consumption and the greenhouse gas emission to form a life cycle environmental burden. And the second is the comparison. We use the relative quadrant metric and the no-dominant sorting approach. Based on the original base method, we can see the right picture. That is the x-axis represents the life cycle cost, and the y-axis represents life cycle environment burden. And the bottom left area defined in the base model represents the high eco-efficiency, and the upper right area represents the low eco-efficiency. And in terms of other alternatives, we can use the no-dominant sorting approach to do some comparison. So based on the calculation approach proposed above section, so we can do the comparative analysis based on under the baseline design scenario. So from the life cycle phase perspective, we can see among the 6 alternatives, in terms of the greenhouse gas emission and the energy consumption and the life cycle cost, we can see the inverted and enhanced semi-rich base and the composite alternative appears to the best design. And from the 5 stage, we can see the raw material phase is the most practical source of the 3 life cycle performance indicator. And from the perspective of the structural layers, we can see the cement concrete layer in the composite alternatives produce the largest greenhouse gas emission and total energy consumption, while asphalt layer shares of the higher life cycle cost, line the greenhouse gas emission and the total energy consumption. And from the materials perspective, we also can see the material, the cement material is a dominant factor for greenhouse gas emission because it accounts about 50% to 90%. And the content of the asphalt layer and asphalt material and cement material involved in the long life asphalt pavement shows to be the key factors in generating the variabilities, such as the foot depths and the composite pavement alternatives. From that analysis, we can see the design parameter change. The signals of the design layer also will be changed, and the same to the greenhouse gas emission and the total energy consumption and the life cycle cost. So based on the baseline design scenario, we investigate the 3 life cycle performance indicator to respond under the various variation in the design parameters. So we investigate 4 critical design parameters here, including the traffic growth rate and the initial traffic volume and the design life and the soil-based response modulus, and the list are their variation range. So from this assumption, we can use the same approach to calculate the sensitivity factors. From results, we can see greenhouse gas emission has the most sensitivity to such 4 design parameters. And we also can see the soil-based response models as the latest influential parameters. where the design life is being the greatest one. And among the six alternatives, we can see the composite pavement structure alternative is the most robust design. And another sensitivity analysis is considering the life cycle inventory data, such as the material rise, and the emission factors and energy consumption factors. So we select 24 relevant life cycle inventory factors, and each factor was decreased by 10% to get the sensitivity factors metric. And from results, we can find some interesting findings. That is, we can see long life cycle cost is more sensitive to the price and the price of the asphalt and the aggregate cost aggregates. While in terms of greenhouse gas emission and the total energy consumption, we can see the most sensitivity parameters is the cement, life cycle inventory data of the cement and the diesel. And also we can see the composite alternative had the most sensitivity to this red color to the life cycle inventory data of the cement. A previous discussion present comprehensive comparisons between the individual alternatives. So to comprehensively evaluate the adaptability of various alternatives under different design contexts, we select 3 levels from the previous design scenario. That is extreme best condition. The middle one is compromise conditions, and the last one is the worst. For example, the best condition means the excellent service environment, and in contrast, the worst means the very harsh service environment. So from results, we can see as to the shared area, we can see in most cases, the enhanced semi-ridge and the inverted alternative can be considered most eco-efficient solution. And when we consider the higher design life, that is, for example, 50 years, we can see the composite alternatives dominant the enhanced semi-ridge based alternative to be the more eco-efficient solution. Another one is when we consider the high traffic volume or high traffic growth rates. This one is a high. This one is a high traffic growth rate is 7%, and this one is the 4,000 initial traffic volume. So we can see the inverted alternative turns out the only eco-efficient solution. Unlike the design parameters, in terms of the life cycle inventories, we assess the adaptability of long life asphalt pavement from the uncertainty perspectives. So we select the unit price, energy consumption, and the greenhouse gas emission factors, and the traffic distance, and a single error range of 5% of life cycle inventory data, and 50% for transportation distance, and to assess the uncertainty. So from results, let's look at the right picture. We can see from the shade area, this shade area means the high eco-efficient solutions. That is the enhanced semi-ridge base and the transitional semi-ridge base and inverted alternative remain to be the high eco-efficient solutions. And in terms of composite alternative and the four types alternative, they have the comparable eco-efficiency and both are higher affected uncertainties. But layer sustainability strength has the latest sensitivity. So from the above analysis, we can see the framework proposed in this study provides a comprehensive analysis of eco-efficiency in terms of the life cycle, in terms of the long life asphalt pavement design, and the results showed that the design and comparison of long life asphalt pavement design and need to consider the economic and environment burden. So the preceding analysis have the following three policy implications. The first one is the context-specific decision making, because as we can see, different eco-efficiency rankings in terms of different alternatives may vary with different economy. For example, price and productivity in the construction context. So we think it is very important to accurately model the uncertainty of the influential factors to make a sustainable design. And the second one is positive utilization of recycled materials. From the above analysis of the sensitivity, so we can see the asphalt materials and aggregates have a significant impact on the eco-efficiency ranking. So if, for example, if recycled materials are available nearby the construction sites, we suggest that they should be utilized as much as possible. And the last one is to optimize the energy structure. From the above analysis, we find the production phase of the long life asphalt pavement is the second critical source of energy consumption. So if we can use some mix, cold mix or warm mix process to produce the asphalt mixture, so that can reduce the heavy oil use of consumption from life cycle stage to further improve the eco-efficiency. Future research can be conducted in at least two aspects. The first is broaden the scope of the eco-efficiency to cover pavement operation stage. For example, layer by layer maintenance strategies based on mechanical, theoretical deterioration model. The second important aspect is to incorporate deep uncertainties into eco-efficiency assessment. For example, recycled material and polymer modified material contents, because with unsustainable materials development, we can use more recycled material or advanced asphalt material to enhance the performance of the pavement structure. The second is intelligent construction utilization proportion. And the final is the clean energy transportation vehicle market share. As to the clean energy transportation vehicle, we can see the clean vehicle will influence the life cycle environment impacts in the operational research. So the scenarios or the sensitivity analysis need to be considered here in a future study. Okay, that's all I want to share with you. Thanks for your listening. Welcome any questions here.
Thank you, Wang, for great presentation. Yeah, so at this point, I'll open it up for questions.
Hi. Hello.
Hello,
I have a
Dr. Yu.
question.
Okay.
So can we go back to the pages that you calculate the environmental cost with the coefficient alpha and beta? Just a clarification.
You mean this page?
I think that's the next page, maybe.
Or this one?
Yeah, this one.
Okay, okay.
I have seen that you calculate the life cycle environmental burden by the coefficient alpha and beta. And I wonder, is it like a empirical coefficients, or you have some model to capture the social willingness to pay, something like that?
Yes, we use empirical coefficient because this is a citation from the 2005. We can actually, if we want to use the best method provide a very helpful framework to conduct the analysis, sensitivity analysis of the coefficient, different coefficients. Yes, because but in here we just use the fixed coefficients to form the life cycle environment burden here.
Okay, thank you.
Okay, thank you, Astrid.
And also I have another question. So,
okay.
Have you considered when you're comparing the environmental burden or environmental cost between the alternatives, have you considered the difference between maintenance strategies between those materials?
I think you mentioned about our future task because actually we didn't consider the maintenance stage because we don't have any practical history data or the theoretical deterioration model. Because as to the long life asphalt pavement design in China, or in except we can use the MEPDG software to model the deterioration model, but I think your question is very interesting because we can know different layer or different material they have different service performance. So yeah, actually we need to consider the maintenance strategy layer by layer. So this is our future task to address these issues. Thank you.
Yeah, thank you so much.
Okay, thank you.
May I just add one comment here? Yes, just to first of all, thank you, Jean, for the question. Regarding to the operation stage, as Dr. Chen has explained here, yes, so we at this moment we didn't explicitly consider the operation stage, but as he also explained earlier, all these 6 design alternatives were designed for the same surface age. So that is one thing that somehow can ease the assumption a little bit, but we do respect that, yes, even with the same design life, the deterioration path can be very different, and then the maintenance strategy in the next 40, 50 years of the design life can be very different. But that's definitely it's a weak point that we plan to do using some kind, hopefully using a mechanistic empirical approach. Yes.
Yes.
Okay, thank you.
Yeah, I think that was tied to the question that I had, which if the design life, if it was exogenous, and I think you just said that it's basically the constraint is that the service life for each of the designs is the same. And so that's interesting. I think that I was going to ask if for each of the designs, if somehow they were optimized for either of the criteria, but I guess essentially here the critical design objective was to basically have these equal service lives. It's a nice study.
Yes.
Yeah, my understanding is that we didn't consider the optimized design yet. We're more kind of a target reaching kind of a design. As long as we reach this critical criteria for those components, we are fine with that. Yeah.
Okay, may I add some comments, because I know that Dr. Prof, his question is also very interesting, because just in this paper, we just consider 6 structural designs under the same design service life. So this is our basic assumption.
See, very interesting. I like. Are there more questions? Can we? Okay. So, I guess with that, I don't have any questions of my own. I think this presentation was extremely interesting. And I guess with that, if there are no further questions, I'd like to thank both the speakers for their excellent presentations today, and for all the participation of the audience. And please look forward to future communications from us on the last spring seminar that will be in a month from now. So again, with that, thank you to our speakers, and look forward to seeing you at the next one.
Okay, thank you.
Thank you.
Thank you.
Thank you.